Hello! For my milestone 2, I wanted to continue my work on deferred shading. I wanted to create a scene that showcased the ability for deferred rendering to support many lights. The scene you're looking at right now has 100 point lights in it, and it can support a directional light source with shadows. For this video, I'm going to show you what I set out to do for my milestone 2, where I started, and show the progression of my project through several videos I took. Then, I'm going to go over the code I wrote to get to the scene that you see here. Here's a screenshot of my Piazza post. For milestone 2, I said I'd demonstrate a scene that showcases at least 50 point lights moving around a scene. The scene will have a single full-screen directional light pass with shadows, and the scene will not include assets existing in the base Prime Engine project. With milestone 1, I had taken all of the data from the G buffer and passed it to a single post-processing pass on a full-screen quad, as it would in a forward rendering pipeline. So the first and most difficult part of milestone 2 was getting a single point light to render. I did this by importing a sphere from Blender as an FBX and then rendering it using additive blending. I used the same shader as the directional light, but instead of passing in directional light data, I passed in point light data with no shadow map. You may notice that when we go inside the sphere, the light turns off. This is because I enabled backface culling without checking whether or not the camera was within the sphere. When the camera is within the sphere and backface culling is enabled, then there are no pixels that contribute to the final lighting of the scene. This is an issue you will see throughout the project for a while, but I fixed it towards the end. The hardest part of getting the point light to render was finding out that I couldn't use the sphere UVs for sampling into the G buffer like I could with the full screen quad pass. This is because the full screen quad, its UVs automatically map to texture UVs, but with the sphere, I needed to convert each pixel back into screen space in order to properly sample from the G buffer. After I was able to get a point light in, I spent about a day importing the FBX files that I needed to produce my scene. I needed something to represent my light. I spawned in 100 static spheres that would eventually move around the scene and have a light on them. I then spaced out the objects more evenly around the scene and attached a point light to each one. Adding a point light to each object was as simple as looping over the code I had already written for a single point light, just with the positions of each sphere. I noticed that the range of each light was too small, and the cutoff was too sharp, so I increased the range of each light to make it more soft. The next thing I did was I added a random color to each light that was spawned using a gradient. From there, I had each light fade in and out using a random offset of time and a varying speed. I wanted my lights to move around my scene, so I started out spawning them all in the same position and having them travel in a random velocity. However, when the lights traveled in the same direction, they would quickly leave the bounds of the scene. So I decided to limit each of their positions to a sphere, having them travel towards the center of the sphere when they left the bounds of it. I thought that there wasn't enough variation from light to light, so I decided to make the color of each light completely random rather than being between two colors. I didn't like the way that the lights were moving around the scene. Their movement was too predictable, and they weren't spending enough time close to the geometry. I messed around with a lot of different ways of spawning them to see if I could fix this. At this point, I fixed the backface culling issue. I tested the camera's position to see if it was within the bounds of the light. If it was, I enabled front face culling. That way, when you're inside the light would still be rendered, and it would not be over-rendered either way when outside or inside the light. I was looking for ways for my lights to move interestingly around the scene, and I came across boids. I followed this 2D example for pseudocode for boids, and I applied it to 3D for each sphere. After a long time of debugging, this was the first result I got with boids. In this scene, there are the same 100 lights, but each light acts as a boid within a sphere. I noticed that since the boids were very close together, the final lighting result ended up as overblown. This is when I brought in ACE's tone mapping in an additional rendering pass. Finally, here's a scene with 10 boids demonstrating that I can support both point lights and a shadowed directional light. Okay, so now I'm going to go over the final code that's in that demo that you just saw. Here's where I'm rendering the point lights. The first thing I do is I get the sphere mesh and I bind it. I bind its vertex index buffers and vertex buffers to the GPU. Next, I create light data. For each of these fireflies, which are really just deferred rendered point lights, I bind their parameters to this light data that is then passed to the GPU. I first get the position and light data for each light. I then assign its position and scale using the parameters found in the light. This function takes each light parameter and uploads it to the GPU. Here's the check where I see whether or not the camera's within the sphere. If it is within the sphere, I cull front faces. Otherwise, I cull back. Then I draw the sphere. Finally, I reset cull face back to GL back, and then unbind the effect. That's the setup work for passing the correct parameters to the GPU when we want to render a deferred light. I can bring up the deferred point light shader. Here's the shader for the point light. It's the same one that's used by the directional light. There are a couple of conditionals that only happen if it's a point light. So if it's a point light, then rather than using the UVs to sample from the G buffer, I use this function to compute the screen space position I can use to sample the G buffer. I do that here. Everything else in the shader is identical to the way that the directional light path with shadows works, except that if it's a point light, I disable shadows. Back to the C++ code. After that, I render another full screen pass to the screen. This pass applies tone mapping to the scene. I found this ACES tone mapping function and I use it to prevent the brights from being capped to 1 on the final scene. Here's where I spawn the lights in the scene. I start off by creating a sphere radius and sphere center. Then, in a similar way to the emeralds respawn, I spawn in these fireflies. These are really deferred point lights with a sphere representing them. I create a mesh instance for each sphere, and then I attach this firefly component. This firefly component takes care of the different aspects of the light within the scene, including its behavior, moving, as well as its light parameters. Here's this firefly or deferred light behavior class that I've created. It assigns its color to a random color, and then from there, fades in and out with a random offset. Here's where we set the fade speed, i.e. how fast it fades in and out, and here is the offset so they're not all fading in and out in sync. Then I give it a random velocity to travel around the sphere. Here's the update function where we can see the boid behavior. Here's where the light code makes it fade in and out, which then gets uploaded to the GPU. And here are the variables used for calculating the boid movement. The first part of the boid movement is trying to avoid other boids. So if it's too close, I use the distance squared function here. Then its velocity will be moved away from the other boids. If it can see another boid, then 1, it tries to move in the same direction as the boid, and it'll try to move towards the average boid position. So here's where I take those summed boid values and I average them out. That's for the average direction and kind of center of mass of nearby boids. Here's where I check to make sure that the boids stay within the sphere. That's why they look like they're traveling around the sphere. It makes them turn in just enough so that they never go really outside the sphere. And then here's where I cap the final velocity between a min speed and a max speed, and then I update its position by adding this velocity to its current position multiplied by delta time. And that's the overview of the code.